Okay, so we've been doing just numbers so far. Let's take a look at x times radical 98x cubed y plus 5 radical 18x to the 5th y. These are not like radicals, so we can't add them, at least not like they are. So we attempt to simplify like we did so it's going to be x radical something plus 5 radical something. Perfect square factors are what we're looking for. 98, that's 49 times 2. X cubed, how did we simplify that last time? When we're looking for a square root, we want the highest power of 2 that we can fit in. So we call x cubed x squared times x. And then y we can't simplify. We can't break up any. So it's just y. Over here, 18. 18 is 9 times 2. X to the 5th, highest power of 2 that fits into 5 is x to the 4th. So we split that x to the 4th times x, and we can't simplify the y. What did I do next? Well, continuing under the radical, and with practice, you might be able to get to the point where you can do some of these steps in your head. That's good if you get there. But you have to understand why we're doing the things we're doing. I'm going to put the perfect squared factors in the front. So here, the 49 and the x squared, those are things we can take square roots of. And then the stuff we can't take the square roots of, that's the 2, the x, and the y. Here, things we can take the square root of are the 9 and the x to the 4th. The things we can't are the 2, the x, and the y. So if we split these up, we have the x, the square root of the 49x squared, and the square root of the 2xy. Plus we have the 5 times the square root of the 9x to the 4th times the square root of the 2x and the y. And since I'm running out of space here, we're going to continue down. Again, if you're taking notes and I'm presenting this to you vertically, please do not write things across. The point of how I'm showing it to you is that that is how you are supposed to show your work. If you're trying to squeeze it all onto a page, you're not helping yourself. Maybe that's how you've always taken notes. Maybe you're running low on paper. I do understand these reasons, but the point of this class is to train you to do math problems and how to show your work and to get you ready for future classes. If you're saying, hey, I'm seeing it this way in the video, but I'm going to write it down some other way, what are you doing? I mean, just really think about that. The act of writing it down is not what's going to help you. What's going to help you is being able to look back at it later. When you get to studying for the test and you come to a problem like this, being able to get to the final answer and understand what happened step by step. If you get stuck, you can then look back at how we did it. You wouldn't need the video for that. Hopefully you're taking notes that are full examples. You're expected to know all of this when you get to the next class. People who struggle in the next class, it's because they don't know how to do the work from this class. This is not a class you want to barely scrape by in. If you're moving on to the next math class in the sequence, this is something you need to know how to do. Anyway, to continue this problem, because we're not done with it yet, I'm going to move this up here, and then you'll keep writing it down underneath. We have this x square root 49x squared, square root 2xy plus 5 radical 9x to the 4th radical 2xy. Let me move that. That angle was not helping. Radical 9x to the 4th radical 2xy. There we go. So what's our next step? Our next step is taking the square root of the one we actually can. So this is going to be x times 7x, because 7x times 7x is 49x squared, times, we can't simplify this one anymore, radical 2xy, plus 5 times 3x squared times 3x squared is 9x to the 4th, times radical 2xy. And then x times 7x is 7x squared. So we have 7x squared radical 2xy, plus 5 times 3x squared is 15x squared, times radical 2xy. Why did I point out that it's just factoring? Well, because even though you can get to the answer of 22x squared radical 2xy, using our 7x squared of these things plus 15x squared of these things method, it might be easier to just say, now hold on a second, I'm going to factor out the radical 2xy. And in fact, I'm going to factor it out and put it on the right side because I know that's where the radical is going to end up. And if I factor out the greatest common factor of the radical 2xy, and I've factored it out to here, what am I left with? What's the leftover piece? 7x squared plus 15x squared. 7x squared plus 15x squared is 22x squared. So 22x squared radical 2xy is the final answer. Now in this one, the 7x squared and the 15x squared were like terms, so we were able to combine them to get the answer. But if it turned out that we didn't have like terms, we would not have been able to simplify any further past that last step before the circle. So if we had 3 radical 5x plus 2x radical 5x, 3 of these plus 2x of these would be 3 plus 2x of these. We can't combine them anymore. You can think of it as taking that common factor and factoring it out to the right. Or if it helps you think of it off to the left, if this is too weird for you, then we're factoring out the radical 5x. What are we left with? 5x times 3 is 3 radical 5x. 5x times positive 2x is positive 2x times radical 5x. And then move this from being the first factor to it being the second factor. Switch the order of the two factors. Because when we write our final answer, we want the radicals at the end. So that's adding and subtracting radicals. We have to make them like radicals. Objective 2 in this topic. Multiply radical expressions. To multiply, to get rid of the parentheses, we must distribute, just like normal. Radical 3 times radical 3. And then radical 3 times radical 2. And we are subtracting. So using the distributive property, then radical 3 on the outside times the first thing minus the radical 3 on the outside times the second thing. Simplify. Radical 3 times radical 3 would be radical 3 times 3, which would be radical 9, which would be 3. Hey. When we do a radical 3 times a radical 3, the radicals go away and we're left with 3. And then radical 3 times radical 2 would be radical 3 times 2, which would be radical 6, and we can't simplify that. So 3 minus radical 6. So the distributive property works. B, radical 3 minus 8 times radical 3 plus 8. When we have binomial times binomial, we have to FOIL. But radical 3 times radical 3 is 3. So we're opening up a new avenue for simplification. Radical 3 times 8 is 8 radical 3. Negative 8 times radical 3 is negative 8 radical 3. The outer and the inner cancel each other out because of this special form. And then negative 8 plus 8, multiply those together, we get negative 64. So 3 minus 64 is negative 61. We have that special formula for a difference of squares. If we notice that one has a minus, the other has a plus, but everything else is the same, radical 3 in the first spot, 8 in the second spot, 1 minus, 1 plus. We can square the first minus square the second because the outer and the inner, when we FOIL, cancel away. Doing so gets rid of all radicals in the problem, leaving us with a numerical answer, that negative 61. So if we multiply something by what is called its conjugate, the radicals go away. So as we move into the next section, we're going to move from adding and subtracting the radicals to multiplying. And as kind of a refresher, the product property, the property that says if we're multiplying two radicals together, we can multiply underneath. That's what's always at play. So we can't simplify radical 6 and we can't simplify radical 10. But if we multiply them together underneath, we get radical 60. And 60, while 6 and 10 might not have been able to be simplified, 60 is 4 times 15. So radical 4 times radical 15 gives us an answer of 2 radical 15. Now remember, we have our special instruction that's always at play. Assume that we have positive real numbers. Here we can see 6 and 10 are positive real numbers. We don't have to worry about any absolute value signs. But our next example is going to involve x. So we do have our special instruction. X represents a positive real number. We don't have to worry about putting absolute value signs in. Let's do one more before we bring an x in. Let's do something in this form. 5 radical 3 times 2 radical 15. Just to point out that these are two simplified radicals being multiplied together. So we are allowed to multiply the numbers and then multiply the radicals. 5 times 2 is 10. And then radical 3 times radical 15 is radical 3 times 15. 3 times 15 is 45. We ask ourselves, can this be the final answer? No, because 45 can be simplified further. .45 is 9 times 5. So 10 times radical 3 times radical 5. Or sorry, 10. I got ahead of myself. 10 times radical 9 times radical 5 is 10 times 3 times radical 5 is 30 radical 5. So 30 radical 5 is the final answer there. Okay, now I'll do the one that involves the x. Multiply the stuff out front together first, and then just multiply your radicals. It's going to look scary. Don't be scared. So the reason I decided to put an extra step in there is because instead of a square root, we're going to have a cube root. 2 cube root of 3x times 4 cube root of 18x squared. Now, these are not like radicals. I apologize for using that term for these previously. What did I say these are called? These are radicals of the same index. They're both cube roots, but that means we can use our property because they're both cube roots. Two times 4 is 8. And then the cube root of this stuff times the cube root of this stuff is the cube root of this stuff times this stuff. So 2 times 4 is 8. And then the cube root of this times the cube root of that is the cube root of this times that. Can't do that with adding and subtracting, but multiplying, we can do that. So 8 times the cube root, 3 times 18 is 54. X times x squared, add the exponents, is x cubed. So pop quiz. Do we look for perfect square factors of 54, like 4, 9, 16, and 25 here? No. If it was a square root, that is exactly what we would do. But this is a cube root, which means we are looking for perfect cube factors. Like like 8, that's 2 cubed, or 27, that's 3 cubed. 54 happens to be 27 times 2. 27 is a perfect cube factor. X cubed is also a perfect cube factor. So we have 8 times the cube root of 27x cubed times 2. That's going to be, we'll keep going down. That's going to be 8 times the cube root of 27x cubed times the cube root of 2. That's 8 times 3x times the cube root of 2, which is 24x times the cube root of 2. Which is the answer. Why is the cube root of 27x cubed 3x? Because the cube root of 27 is 3 and the cube root of x cubed is x. So hopefully you are seeing why it is important to understand every lecture before moving on to the next. There was a lot of stuff with radicals in the last one. If you didn't understand it then, now you have to understand it in addition to the new material, because the last section is now a part of the sub-steps of this section. And now everything about adding, subtracting, and multiplying radicals, you need to know, because if we ever see radicals moving forward, and we will, not just in this class, but also the next class, next course, next math course past this, you're expected to know how to do all this. If not, that becomes really difficult, because this is the time to learn this. Next lecture is the time to learn something else that requires you to know how to do this. You might only need a C to move on to the next course, but being completely honest with you, you want as close to perfect knowledge of this stuff as possible, or the next class is going to be very, very, very difficult. Okay, let's make the multiplication more advanced now. Let's say we have 3 radical 11 times radical 11 plus 2. Well, we can't add together radical 11 plus 2. They are not like radicals, so we can't add them. And there's no way to simplify them to be able to combine them in any way. But what do we do if we had 2 times x plus y? We can't add x plus y, but we need to get rid of the parentheses. How do we do that? We distribute. So it would become 2x plus 2y. It's the same thing we do here. But we need to be careful, because something happens, could be described as magical, when we multiply a radical times a radical, and especially when it's the same. Let's not do too much in one step. 3 radical 11 times radical 3 radical 11 times radical 11 is 3 radical 11 times radical 11. I'm not actually doing it yet. And then 3 radical 11 times positive 2 is going to be positive 3 radical 11 times 2. Just so you can see. Radical 11 times radical 11 is the same as radical 11 squared. So the square and the square root cancel each other out and just leave us with 11. So radical 11 times radical 11, a radical times itself just leaves us with what's underneath. Plus 3 radical 11 times 2 is 6 radical 11. 3 times 11 is 33. 33 plus 6 radical 11 is our answer. So that's how we use the distributive property when radicals are involved. Let's do another. Five radical x times 2 radical x minus 3 radical y. We have our special instruction at play. Assume all variables, so assume x and y, represent positive real numbers. We don't have to worry about any absolute value signs or anything like that. We distribute. 5 times 2 is 10. Radical x times radical x. I'll leave that unwritten out for now. 5 times negative 3 is negative 15. Radical x times radical y. I'll leave that undone for now. A radical times itself is just what's underneath. Radical x times radical x is just x. Minus 15 radical x times radical y is radical xy. That's the answer. 10x minus 15 radical xy. Let's keep going. Let's take a look at multiplying two radical expressions together that resemble binomials, so two terms each. Radical 5 plus 3 radical 2. And we're going to multiply this times 2 radical 5 minus radical 2. If this was something like x plus 3 times x minus 4, what would we do? We would FOIL. First, x times x is x squared. Outer x times negative 4 is negative 4x. Inner positive 3 times x, positive 3x. Last, positive 3 times negative 4, negative 12. Then we'd combine like terms. Minus 4x plus 3x, that's negative x. Minus 12. But first, outer, inner, last. FOIL. It's just double distribution, but FOIL is how people remember this. the first terms, the outer terms, the inner terms, and the last terms, and you're careful. You're careful to use the signs in front and keep track of your signs. First, that's radical 5 times 2 radical 5. Outer, that's radical 5 times negative radical 2. Positive times negative is negative radical 5 times radical 2. Inner, positive times positive is positive 3 radical 2 times 2 radical 5. So I'm not actually doing any of it yet. I'm just setting up. First, outer, inner. Last, positive times negative is negative 3 radical 2 times radical 2. So notice when it was radical times radical, I can just put them right next to each other. But if the radical was ever multiplied by something with a number, I have to indicate that there's some separation. So one way of showing separation is using the multiplication dot. Another way of showing separation is by putting each piece of the multiplication in parentheses. So let's start simplifying. Now, if you can grasp how to do each of these pieces, then you don't have to write this step out. When you're doing your FOIL, you can go first, radical 5 times 2 radical 5 is 2 times 5 is 10. Or once it's all written out, we can just look piece by piece by piece by piece. All we have is the 2, and then radical 5 times radical 5. Multiplying a radical by itself leaves us with what's underneath. 2 times 5 would be 10. Minus radical 5 times radical 2 would be radical 5 times 2, which would be radical 10. And we can't simplify radical 10 at all. Plus 3 times 2 is 6. Radical 2 times radical 5 would be radical 2 times 5. So plus 6 radical 10. Minus 3, and then radical 2 times radical 2 is just 2, because a radical times itself just leaves us with what's underneath the radical. So minus 3 times 2 is minus 6. Finishing up simplifying, 10 minus 6, positive 10, negative 6. 10 minus 6 is positive 4. And then negative 1 of these radical 10s plus 6 radical 10s would be negative 1 plus 6 of the radical 10s, which would be positive 5 of the radical 10s plus 5 radical 10. So 4 plus 5 radical 10 is the answer. Under no circumstances are you to make this 9 radical 10. If you see this 4 plus 5 and you think that means that you need to make it a 9, you deserve no credit on the entire problem. Honestly, if you got through every bit of it and then came to the end and said 4 plus 5 is 9, so 9 radical 10, you would get no credit and you would deserve no credit. Because even though you went through all of this, and by the way, the only new thing is what do we do when we multiply a radical times a radical? Everything else here we did back in the section where we multiplied polynomials. But then if you come to here, 4 plus 5 times radical 10, and you violate order of operations, which says you multiply before you add, therefore this is a thing that is kept together because multiplication comes first. You cannot add 4 to this and end up with 9 radical 10s. You cannot combine these. They are not like radicals, so you cannot add them together. If it was 4 radical 10 plus 5 radical 10, then you'd have 9 radical 10. But 4 plus 5 does not become 9 in this instance. You cannot separate the 5 from the radical 10 because multiplication comes first. So this is joined together. And we know how to add radicals now. Let's look at another. Three radical x plus 5 radical y times 2 radical x minus 7 radical y. Again, let's FOIL. First, 3 radical x times 2 radical x. Outer, positive times negative is negative, so minus 3 radical x times 7 radical y. Inner, positive times positive is positive, so plus 5 radical y times 2 radical x. And then last, if you have more room off to the right of your page, please write it next to, but I'm going to put it here. Positive times negative is minus 3 radical x oops, sorry. Not the 3 radical x. First, outer, inner, we're doing last. Positive times negative is negative. 5 radical y times 7 radical y. Okay. 3 times 2 is 6. Radical x times radical x is x. Minus 3 times 7 is 21. Radical x times radical y is radical xy. Plus 5 times 2 is 10. Radical y times radical x, that's still radical xy. And then minus 5 times 7 is 35. Radical y times radical y is just y, because a radical times itself is what we're left with underneath. Negative 21 of these radical xy's plus 10 of these radical xy's, those are like radicals, so just like terms, we combine. We end up with 6x, negative 21 of these plus 10 of these is negative 11 of these radical xy's minus 35y. And that's the answer. 6x minus 11 radical xy minus 35y. Does squaring do the same thing? Well, if we FOIL this with itself, radical x plus 1 times radical x plus 1 is x plus 1. Radical went away. And then outer 2 times radical x plus 1, and then inner 2 times radical x plus 1. We add those together, we get 4 radical x plus 1. The radical did not go away. Last would be 2 times 2, which is plus 4. So we have x plus 1 plus 4 radical x plus 1 plus 4. And be careful, at no point combine this 1 plus 4. That 4 is attached to the radical. You can add the 1 to this 4 over here. In fact, let's do that. X plus 5 plus 4 times radical x plus 1. But we can't make that x plus 9. That 5 and that 4, they can't add. They are not like radicals. And that's it for this topic. The topic is rationalizing denominators and numerators of radical expressions. The first objective in this topic is rationalize denominators. Many times it's helpful to rewrite a radical quotient with the radical confined to only the numerator. If we rewrite the expression so that there is no radical in the denominator, it's called rationalizing the denominator. This process involves multiplying the quotient by a form of 1 that will eliminate the radical in the denominator. Last time we looked at a problem like this, where we have a binomial that involves a radical, and we multiplied it by another binomial that involves a radical. For today's first example, we're going to look at a binomial times not just any other binomial, any other two-term thing that's involving a radical. It's actually going to be itself. And what did we do? We FOILed. First, 3x times 3x is 9x squared. Outer 3x times radical 2 is positive 3x radical 2. Inner, that's another 3x radical 2. And last, radical 2 times radical 2, that would be radical 2 times itself, radical 2 squared. We're just left with the 2 that's underneath. And here I've written 3x radical 2, but the reason I've done that, is because I like it when the radical is at the end. We don't have that confusion. Technically, the coefficient of x here would be 3 radical 2. This is 3 radical 2x. But when we write it like this, there is very easily going to be confusion between this and what is definitely not the same, 3 radical 2x. Where does the radical actually stop? We avoid that altogether by making sure that the radical factor is written last. So instead of 3 radical 2x, 3x radical 2. Anyway, what is 3 radical 2 plus 3 radical 2 in order to combine these like terms? Because 3 radical 2 x's plus another 3 radical 2 x's. Well, they're like radicals, and 3 plus 3 would be 6 of the radical 2's. So when we combine here, we get 3x plus 3x equals 6x radical 2 plus 2 on the end, and then the 9x squared in the front. So like I said, this way of writing it, that's for most clarity, but also correct would be 9x squared plus 6 radical 2x, being very careful that that radical 2 or that radical sign does not extend over the x, plus 2. Why am I starting with this today? Well, what does it mean when we write something times itself? It means squaring. What I want to drive home here is a fact that radical A plus radical B squared would not be A plus B. Now, radical A times radical B squared, or radical AB squared, would be AB. That works for multiplication. It works for division. It does not work for addition or subtraction. And this should be all the proof you need. Here, we're squaring radical terms. And do we get the two things under the radical as the answer? Do we get an answer with no radicals? No. We get a 3-term thing, not a 2-term thing, a 3-term thing, and the second term still has a radical in it. This may seem like a weird thing for me to be pointing out right now, but like I said, as we continue with the examples, you're going to see why I'm bringing this up. And we didn't have to FOIL. Remember that when we have a binomial squared, we have a special formula. Square the first thing, so square the 3x, plus in the binomial, so plus here, 2 times the two things multiplied together. 2 times 3x would be 6x times radical 2. Well, I don't want to do that yet. Let me just write it out. 2 times the first times the second, and then always plus, no matter what's inside, the second thing, radical 2 squared. Squaring 3x gives us 9x squared. 2 times 3x, that's the 6x, times radical 2, that's our 6x radical 2, or 6 radical 2x. And then radical 2 squared, square root squared leaves what's underneath. There's our plus 2. So remember, we do have that formula for a special product. Square the first, and then plus or minus whatever's inside, and then 2 times the first times the second, and then always plus no matter what's inside, and then square the second. It's a shortcut. Makes things go a little faster. What was the other special product that we have? Well, another special product we have when we multiply binomials was the multiplication of conjugates, where we were multiplying two things that look exactly the same except for one difference. That difference is one of them is adding the two things, the other is subtracting the two things, but the two things themselves are the same. Remember, that was a plus b times a minus b, and we got a squared minus b squared. It's the difference of squares formula. Multiplication of conjugates gives us a difference of squares. Just like if we factor a difference of squares, we get two things, one plus, one minus, conjugates. Multiplying these does give us a two-term thing. And when we square these things, that should get rid of the radicals. So this one would give us a two-term thing with no radicals. Let's do the long way first, though. Let's just FOIL it. Foiling would be first 4 radical 5 times 4 radical 5. And then outer 4 radical 5 times negative radical 6. 4 radical 5 times radical 6 with a minus, because positive times negative is negative. Inner, that's going to be plus 4 radical 5 times radical 6. If you have them in the other order, that's okay, but they are still the same thing. And then last, so we just did inner, now we do last. Positive times negative is negative, radical 6 times itself. These terms are the same, they cancel each other out. So we're left with 4 radical 5 times itself, or 4 radical 5 squared, and then minus radical 6 times itself, or radical 6 squared. And that's that difference of squares formula. We can skip over the foiling step when we have this special product. We can skip over the foiling and we can go, hey, these are two things that are exactly the same, except one's adding them and the other's subtracting them. That means they're conjugates. It would be the first thing squared minus the second thing squared. It's always a difference of squares. There is no such thing that's going to give us a sum of squares, at least not with the real numbers. We'll see what happens later on today. Okay. So the first thing, 4 radical 5, the second thing, radical 6. Same thing we got with the foiling. Let's finish that up. Squaring 4 radical 5 would be squaring the 4. 4 times 4 is 16. And then squaring the radical 5. Radical 5 times itself is just 5. Minus. Radical 6 times itself, that's 6. 16 times 5 is 80. 80 minus 6, 74. So we multiplied two things together that involved radicals, and because it was this special setup, this multiplication of conjugates, the radicals went away. Again, it might seem weird that I'm pointing out that specific thing, but you're going to see why as we progress. I want you to consider the expression 1 over radical 2. Now, radical 2, if you took the square root of 2 on a calculator, would be 1 over estimated 1.414. And if we wanted to actually divide this, 1 divided by 1.414. Now you might be saying, hey, that's no problem. I just used the calculator for the radical 2 to get the 1.414. You shut up now. You shut up with that. I'm trying to make a point here, and it's a good point. So let's forget about the fact that we used a calculator for this. Now we're back in, let's divide by hand land. So first of all, we wouldn't be allowed to have a decimal on the outside. So 1, 2, 3 spaces over. Here would be 1, 2, 3 spaces over. End up here. We'd have to look at 1,000 divided by 1414. So complicated. Makes me not want to do it at all. Now, what if I told you that 1 over radical 2 could be expressed another way? It could actually be expressed as radical 2 over 2, and I'll show you how to do this in just a second. I'm going to tell you why it's important first. Radical 2 over 2, that's 1.414 whatever divided by 2. I could really quickly say that that's about 7.707. Just kind of took half. Dividing by 2 is easy, even if you did it by hand. So it's easier to divide by a number than it is to divide by a radical. So the convention is we don't want radicals in the bottom. We don't want that. So what we're going to do depends on what exactly is on the bottom, what the situation is. Our strategy is always going to involve the fact that anything times 1 is itself. We just have to be clever about the form of 1 we choose. Anything over itself is 1. So we want to multiply by something over itself in a way that rewrites this as something that does not have a radical on the bottom. It turns the bottom from an irrational number to a rational number. And that's why this process is called rationalizing, wait for it, the denominator. Wow. Rationalizing because we're turning something irrational into something rational. Not the whole thing. It still has a radical. It's still going to be irrational overall. But what will be rational is the denominator. Right now, it's not. Hey, this is just a square root. A square root times itself leaves us with what's underneath. And since we're supposed to be multiplying by 1, if we want to multiply by the square root of 2 on the bottom, we multiply by the square root of 2 on the top. 1 times the square root of 2 is the square root of 2. That is how we got that earlier. Let's do another. If we have 2 over radical 3, that's bad. We want to rationalize the denominator. We don't want to write our final answers with radicals in the bottom. Well, this is a square root of 3. If we multiply by another square root of 3, that'll just leave us with 3. And since we want to be multiplying by 1, radical 3 over itself. So 2 radical 3 over 3 would be 2 over radical 3 in rationalized, with a rationalized denominator. Now, by the way, there might be a specific problem at some point that wants you to rationalize the numerator. That would just be the flip of this. We wouldn't want any irrational numbers in the numerator. That is very uncommon. It would be specifically asked for, and it would just be training you for later on when it might be an easy step in a larger problem. That's well beyond this course. But the idea of being able to rationalize, whether it's the denominator or the numerator, that is what we're focusing on here. It's what you should be able to do. Let's say we had the square root of 1/8. Now, at first glance, you might be thinking, well, what about the square root of 1/8? What's wrong with this? Well, what's wrong with it is when we see the square root of an entire fraction, we know that means that we can have square root over square root. And that means that hiding in square root of the fraction is in fact a radical in the denominator. We need to deal with that. We can simplify a little first because the square root of 1 is just 1. So what we're really looking to rationalize when we are looking at square root of 1/8 is 1 over the square root of 8. And if we multiply that by the square root of 8 over itself, multiplying by 1, that's going to give us square root of 8 over 8. Cube root. Cube root, let's look at the cube root of 64 over a. Again, fractions inside of the radicals means that hiding is a radical in the denominator. Ooh. Cube root of 64 over cube root of a. There we go. Just avoiding the light spot. And the cube root of 64 is 4. So what we're looking to rationalize is 4 over the cube root of a. Now here, we can't just multiply by the cube root of a over itself. Because unlike a square root, where a square root times a square root does get rid of the radical, because it's a square underneath a square root, and the square root cancel away. It's not a square that cancels a cube root. What is it? Oh, and this, oh, that's a mistake. That is 3 square root there. That's what I warned you not to write. Let me make sure that 3 is inside the little pocket. We would need yet another cube root of a. Why? because a cube root of a times a cube root of a times a cube root of a would be a cube root of a cubed. And those do cancel and just leave us with a. But what would we have on top? We would have 4 times 2 of these. But it wouldn't be 2 cube root. That would be if we were adding. It would be the cube root times itself. Or the cube root of a times the cube root of a is the cube root of a times a. Cube root of a squared is how we would write that. 4 cube root of a squared all over a. I'm going to do another. This time I'm going to do the 4th root of 16 over b. Which would be the 4th root of 16 over the 4th root of b. And the 4th root of 16 is 2. We need to rationalize to get rid of the 4th root of b on the bottom. How many more would we need? Well, we would need the 4th root of b cubed, because that's what gives us the 4th root of b to the 4th. B times b cubed is b to the 4th. So we need a 4th root of b cubed on the top because we're multiplying by 1. And let me actually move this down here so I can actually write that without, 2 times the 4th root of b cubed. There we go. So again, that top is 2 times the 4th root of b cubed, and on the bottom, the 4th root of b to the 4th would be b. Assume that all variables are positive real numbers, of course, and then we don't have to worry about the absolute value signs.